All right, welcome everyone. Today is going to be a fast-paced introduction to our coding environment and some tricks that you're going to use. And so I'm your TA. I'll be holding 2 office hours per week and 1 floating office hour that's up to you to schedule. You can just email me and I'll see some time that fits the majority. We have 50 minutes. And at the end, you'll end up with the homework 0. It's not mandatory. You can practice some coding, but we'll be providing some feedback on Canvas. So if you're not familiar with Python, NumPy, scikit-learn, it's a good opportunity to get some practice before starting homeworks. So I'll be presenting the required tools. I'll be talking about JupyterLab, Jupyter Notebooks, NumPy, Matplotlib, and scikit-learn. So these are basically standard libraries that everyone who does machine learning will be familiar with them. And at the end, which be the K nearest neighbor classifier, I'm aware that Claire is still in the middle of that part, but I expect by Monday you have a clear idea. But for now, we'll not be implementing the internals of KNN. We'll just be using the implementation from scikit-learn, just to give you a flavor of what scikit-learn does. All right, so the Python version we'll be working with is 3.9, 3.10. We'll be making sure that all assignments are compatible with these versions, so you should not have an issue. We'll be using Jupyter Notebooks for 2 reasons. Is that you can code in Jupyter Notebooks and you also can type. And if you're familiar with LaTeX, it's really good for typing equations. It's going to be very simple syntax, no integrals or partial derivatives, so don't be scared. All right. Okay, so the main idea here is that in each assignment, we'll be in the header of the Jupyter Notebook, we'll be providing all the packages that you'll be using. If you find some package out there that answers the question directly, okay, 1 second. It's weird, it does not show. Display. Scale like this. Yeah, because my screen is 3x4, it's not. Anyway, let's find something that. Okay, we'll cheat this way. All right, so the idea here is that all Jupyter Notebooks will have the packages that you'll be needing. I'm sure there's some packages out there that answers the question or the assignment in probably 2, 3 lines. Usually you'll not be allowed to use that. But if you find some helper functions out there and you're not sure, just ask on Piazza. You get a straightforward answer. Okay. Yep. So if you have questions about setting up environment, we will only be helping you if you use Anaconda and nothing else. Okay. There are so many ways out there. You can use Vim, virtual environment. There are so many tricks, but we'll only be helping you with Anaconda. So as I said, there'll be a notebook that you are welcome to submit if you need some feedback on how to optimize things. You can also use Google Colab, which is basically you can upload your notebook on Google Drive and just open it there and work on it. The problem with Google Colab is that your notebook can be shut down at any time if you are inactive. So if you start your assignment at the last minute, which is usually the last day, you might have some problems. And you'll be sending emails, oh, my instance was shut down. So if you're Google Colab, make sure you do that. Sometimes you have to produce some files, and on Google Colab, if the instance is shut down, you will lose the files. So be aware. Yeah, if you use Google Colab, I expect you are already familiar with the pip command, which means that in Google Colab, the packages are not installed by default, so you have to install the packages by yourself. Okay. So starting with Anaconda, if you go to the link or just Google anaconda.com, you'll be going to this page. For me, they will give me a Linux distribution. If you use Linux, then you already know how to proceed. In Windows, it's just a simple installer, and Mac is the same thing. If you're on M1, from experience, you have to use the M1 installation because it's not the same architecture, and not all packages are compatible between the two. So that's going to save you some hours. Okay, so in my case, I already installed Anaconda on my laptop. Okay, let me just go to the terminal. Okay, I'll be using some shortcuts, not too many, so it's good if you keep track of them. I believe the class is recorded, so you can always go back and try to see what the trick is. Okay, let's start. So with Anaconda on Windows or Mac or Linux, you can have, what was it? Okay, let's see. Forgot the command. Okay, it was Anaconda Navigator. If you're on Windows, you should just have an icon. All right. Okay, so when you open Anaconda Navigator, you're getting this interface. You have a lot of tools. You're welcome to use any one of them. I recommend PyCharm Professional. If you're a student, you can get 1-year license that you can renew as long as you're a student, and you get a lot of hints, a lot of tricks to avoid some errors, because sometimes you have a global variable that you use inside the function and things don't work. So PyCharm will point you to that. Spyder, I've seen some students use Spyder. It's very painful for Jupyter notebooks. I don't recommend. And then you have Jupyter Lab. Jupyter Lab, just an interface for Jupyter notebooks, but with some terminals and folders that you can basically see the folder where you are working. The other tools I have never used. Okay. I recommend starting from Jupyter Lab. Okay. All right, so if you open Jupyter Lab, it should look like this. You are either welcome to start the notebook immediately, or you can use some tricks like terminals. The advantage of Jupyter Lab is that you can see the folder where you are working, so you can do some file manipulation. And okay, I'm not going to wait for you so that everyone has already installed Anaconda. On the other hand, you can always go to the coding CS department environment, and there you have the Jupyter Lab already ready for you. Okay, so we'll be starting from there. All right, so one trick you might find very useful if you're working on your laptop. Okay, let's say you want to run the notebook, or you want to do the assignments on your laptop and not on the cloud, okay? One thing that I recommend using is what you call the environments. So a Python environment is just an isolated room where you choose which packages you want to install, okay? So here I can just do conda, sorry, just zoom in, okay. Conda inv list. It should give me a list of environments that I have. Here I already created environment lab 1, okay? So I can just do conda activate lab 1. All right. So in lab 1, I can do conda list, and I'll be getting all the packages that I have on lab 1. For instance, I have scikit-learn already installed, and I have NumPy, okay? Why is this useful? Because, for example, you have you're doing deep learning in PyTorch, and you have different versions, and you don't want to mix the different package versions, so you can have different environments with different dependencies and settings. Okay. So if you're on a laptop, I advise that you do that. You can do like conda create, and I call it like homework 0. Okay? You can also choose which Python version you want. You can do like 0.9 or 0.10. 0.9 is safe. It's more mature. Okay? So these are the default packages that will be installed. There you go. Now I do conda in list, and the environment should be there. There you go. And now I can do deactivate just to leave the lab 1. Okay. 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 Now I left lab 1. I can do. Okay. Now I'm moving to homework 0, and here, since I haven't installed anything yet, NumPy and scikit-learn are not there. So you have to install them. You can do like conda install and then list the packages. Okay. All right. Now going back to my CS coding environment, it's the same JupyterLab that you get on your laptop with a few more tools. Okay, let me go to the slides. All right, we have been through this. I have showed you these through them. Okay, so let's get started. You have 3 ways to get today's notebooks they're going to work on. You can either go to Canvas. There's a lab 1 zip file in the modules. You can go to the repo here, and there you go. You find lab 1 extracted, or as I like, I will just go copy this, and I will go to the JupyterLab, open the terminal, and paste down. Okay. All right. So now if I refresh, I have the folder added here, and I have the lab 1 folder. It's much easier. Okay. All right. Who's already familiar with Python? Who's new? Okay. Familiar? All right. New? Perfect. Okay. I'm not going to go into details. All right. So we'll be working with NumPy package. It's a package that does matrix manipulations and some probability, like generating random variables. You can do interpolation, anything that you have seen usually in linear algebra and analysis. Not signal processing, so there's no Fourier transform here. It's fast because it's coded on C, C++. So it's basically just an interface with the C and Python code. So it's much faster than looping, for example. Sometimes 100 times faster, so depending on the size of the matrix. We'll be using also a module called linalg, which is short for linear algebra, to do like inverse matrix, QR decomposition, Cholesky. You can imagine all the decompositions you have seen. And yeah, anything you can imagine in linear algebra is there. Okay. So, who already worked with matrices? 1, 2, 3, 4, 5. Okay. I have an experiment, but let's see if it works. Try to go to this link. I'll just go there myself. What's that?
Can you just put the link back up again? Or just swap the tab?
Oh, the link?
Yeah.
Oh, sorry. Yeah, I thought everyone copy-pasted. All there, let's see. Yeah, you have more than 10 people, that's good. So here we'll be coding together, and You're free to go ahead in the last cells if this is too easy for you, but let's see. If you have some comments or questions, you can just type them there or let me know. All right, so we are importing NumPy, and then we'll be using linear algebra. First thing is matrix addition. So we want to add two matrices. What's the condition that we should be satisfying? Assuming that the matrix A is m by n and B is p by q. What's the condition that should be satisfied so that the matrix addition is correctly defined? Yeah. So the table should be equal. M equal P, N equal Q. So for example here, I just have to do like 3, 2. Okay, something strange here. Okay. Okay, 1 minute. All right, so let's run the instance. It's probably a 1-core CPU. Anonymous user is in this. Please don't. Okay, so what happens here is that I'm using NumPy to generate random matrices of integers between 0 and 4, 4 included. So if I do 5, it means it's from 0 to 4. So if you have to generate indices, be careful. There are some mistakes that happened last year. And what does this seed 0 do? So I'm going to just comment this block. Okay, forget it. This is not working. All right. So it said it's just be two, like, same shape. So I'll be 3, 2. All right. Let's import. Okay. And let's look at matrix A and B. So these are the matrices. If I run this cell again and again, I get the same results, even though I said it's random. And that's because of the random seed. So here, if I fix the random seed, it's basically I'm fixing the starting point of the random number generator in NumPy. And if I comment this line, then each time I'll be getting different results. Okay? And this is important if you want to get the same output or results in different PCs or laptops, or you want to fix the random seed. Otherwise, you're going to have different results at each random time, at each run. All right? And, yep. Once the A and B have the same shape, addition is straightforward. And now I want to do matrix multiplication. So the condition here is that the number of columns of A should be equal to the number of rows of B. It's very simple, but you'll be surprised how many complaints we get. So in this case, N should be equal to Q, okay? And you can check that it's definitely correct. So I have an error here. I have put P, okay, so. All right, okay, so this is matrix multiplication. Make sure the number of columns of A is equal to the number of rows of B. One thing to be sure, especially when you debug, you can always do A.shape and B.shape. So when you do this, you get the size of the matrices that you're working with, okay? So if they're given to you and you want to debug, you can use that one. Okay, so now I want to inverse a matrix A. So the condition for computing an inverse of matrix that has to be square, okay? So in this case, I have to make sure that M equals N. I'll choose 3 just to make it easy. And this is my matrix, all right? Before I invert the matrix, usually in linear algebra, you have to make sure that A is invertible. So how do you do that? How do you check if a matrix A is invertible? Yeah, so Yeah, you check the determinant. So in this case, I can just use linear algebra, and I can have the determinant. In this case, it's -6. Okay? It's not always the case. So if I change the random seed to 17, you see that the third row and the second row are collinear. Okay? So in this case, the rank is definitely not 3. So if I go determinant, I expect 0. Okay? So in this case, if I try to compute the inverse, it's not going to work. I get some error. All right, so let's just go to 42, safe. And let's get our inverse matrix here. Okay, so this is the inverse of A. Usually, when you get a matrix A, or if you basically in an math exam and you ask to compute the inverse to check that your result is correct, you have to check that A dot the inverse is equal to identity. Okay. All right. So in this case, if I run it, I get almost the identity. Okay. One thing to use is you can do like NP is close. We're just using NumPy. And then I want to check if it is close to the identity 3. Okay? So it's all through. There is a precision here. Sometimes you don't want to check if it is exactly the same or up to 10 to minus 15. Instead, you can just use absolute tolerance. So, for example, let's say 10 to minus 5. Okay. Let's show you an example here. Just do NP is close and do like 1, 0.9. I expect to get false, but if I do atol 1 minus 1, it should be true. So you can define the tolerance that you'll be using. Okay? All right. So one thing I wanted to show you, since you had something related to eigenvectors in the quiz, you can also use linear algebra to compute the eigenvectors and eigenvalues of A. Okay? So in this case, you're going to use lena.eig for eigen. I had something to say about this. Yep, you have to make sure that A has real eigenvalues, otherwise you're going to get some complex results. In this case, we're safe. I checked before. Okay? So alphas here will be the eigenvalues, and X will be the matrix of columns of A, or basically, so the first eigenvector is going to be this, second, and third. All right? Let's do a sanity check, which is usually just run A.x. Okay? And now I want to check that these are proportional to X with the same eigenvalues that I got. So here I already see that X does not have any zeros, so it's safe. I can just divide by X. So this is element-wise division. Okay? It's not the left matrix multiplied by the inverse of the right one. Okay? So in this case, you can see that we get almost the same eigenvalues here. So these are definitely working. Okay. We have seen matrix addition, multiplication. One thing I want to add is multiplication by scalar. So I have matrix A, and I want to multiply it by 3 or 4. I can just do this. Okay? It's as simple as that. You just multiply by scalar, and you get the matrix multiplication. All right. One last thing. This is going to happen sometimes in the assignment. So let's say I have change A. I have a function that takes A, and I want to change just the first column of A. Okay? All right, so I have my matrix A here. Okay? And now I will do change A. Okay? And now I want to look at A. Okay? you see here that the change I have done to A inside the function is saved. Okay. So if I take matrix A, I just replace the first columns by 1, then the change persists. Okay. So these like column or row manipulation is going to be saved to A. To make sure that you're not doing this kind of crime, you can just do A equals A.copy. Okay? So let's just go back and run my definition of matrix A. And now, since I'm working with a copy, the change is not going to be affecting matrix A, but the copy that I have inside the function. Okay? So keep this in mind. All right. Now I will be introducing a new player, which is the matplotlib. This is the standard one in Python to do some plots and figures, so you can get used to it. There's another one called Seaborn, which is a wrapper around the PyPlot, and you are free to use whatever plotting library that you like, as long as it's standard, not something it's like closed source or something. Okay. So before I used a random integer, so in this case it's going to be random floats between 0 and 1. This is a uniform distribution. I guess everyone's familiar with it. So what happens here is that I generate a matrix that is 64 by 2. And what I mean here is that I'm generating basically 64 samples in the space of 2D. Okay? And then I'm defining y as 1 if x0, which is the first column, or the x coordinate, is larger than the y coordinate, and 0 otherwise. Okay, this is basically y. And then I'm going to add some noise to x. So after defining y, I'm just going to add some noise. And this is my plot. I'm guessing the violet ones are 0 and the yellow ones are 1, but we're going to see later. Okay. If I remove this one, if I just run this without the noise, yeah, they are basically clearly separated. But when I add the noise, there's some overlap in the regions. So in the next 20 minutes, I'm going to show you how to use scikit-learn to get a linear model, or basically you're going to try to find a linear boundary or linear boundary decision between these two classes. And for that, we are going to use what we call a perceptron. You don't have to learn or know what perceptron is. You can just assume it's kind of a magician that works with straight lines. And, okay, the link here is wrong. But anyway, so in this case, we'll be using perceptron or ridge classifier if you go to the documentation, which I really advise you to get used to. Everything is explained here. But for us, this is magic for us at this point, so we're not going to bother with this. What's important is only the Python part, which is what are the different parameters that you initialize, what are the attributes of this object or this class, and the methods. And the methods are here. Okay? So you have fit, you have predict, you have score, you have decision function. And the attributes, we want to look at coefficient and intercept. Okay? So what happens here is that I'm just importing the ridge classifier from the linear model module of scikit-learn. So linear model is going to have any model that's based on a linear boundary decision or some linear operations. Okay, it's if you go to the official website, I can just click linear model, and there you go. You have so much. You don't have to bother with those. After class, you're gonna know most of these concepts. So you're gonna see, okay, there's a lot of redundancy. It's no longer magic. All right, so here I define the linear classifier. It's there, and I call the fit method. In scikit-learn, as I explained here, all models have a fit method and a predict method. So in the fit method is where you provide the information. So in this case, I'm providing the samples and the labels, okay? In unsupervised learning, where you don't have labels, you're not going to provide Y, okay? You're just going to do fit X. And the predict method is where you query that model to get the predicted labels. And so you can assume that the X you have in predict is different from the fit method, but in this example, they are the same. Not too complicated. All right, I run that, and I define my linear classifier, and I provided the information that it needs. Sometimes you're going to see some functions like these. These are just helper functions to help you save some time. We don't want you to do Python. We want you to do machine learning. So we're going to provide a lot of these to help you just concentrate on the machine learning part. Okay? So what happens here is that I provide the data points, the model, and axes. Axes is basically an object from the matplotlib. You're going to get familiar with it later. So here I define the figure and the axes, and I want to plot the decision surface. What this does is that just it goes from the all range of x's and the x-axis and the range of xy. It creates a mesh grid, and then it predicts the label at each point of that mesh grid. Okay? It's not magic. Once I run this cell here, there we go. This is my mesh grid, basically. So I have the points ranging from minus 0.5, around minus 0.5 until 3.5. And I trained the model, so the boundary here is the line that will be separating the two classes. And if I'm correct, I'm missing basically 2 blue points that I'll be classifying as 1. Okay? So I have 64 points, and I'm misclassifying 2. So I would be expecting to get, sorry, not 2. Yeah, 3. Yeah. So 3, I'll be expecting to get some accuracy of 61 out of 64. All right? Okay. So what happens here exactly in this classifier? What happens here is that the label 0 will be actually converted to -1, and the label 1 is going to remain 1, okay? And this model will be trying to learn this line so that the score associated with the ones on the left is negative and the other ones on the right is positive, okay? And these scores are defined linearly as some. Is this? No. Okay, let me just do this. All right. So this model basically tries to learn the weights W and the weights and the intercept or offset B, okay? And these are exactly what's defined here as the intercept and the coefficient, okay? So remember that we are working in 2D, so the number of features is 2. Okay, so expect W to just be to have two elements. B is just going to be a scalar. So we can just check that. We can W shape, B dot shape. Okay. So now we want to compute our own scores. So in this case, I'll just do scores. I know that X is 64 by 2. Okay, so I can do W dot and X, but for the product to be defined, I have to transpose, and it's pretty easy in NumPy, just do .t, okay? So that's the transpose, plus B. All right, so let's just check the score shape. I expect it to be 1 by 64, if my math is correct. Okay, and now I just want to print what's the scores of the first 10. So this is basically a 1-row matrix. So I'm going to do 0, and I'm going to go up to 10. Right. I know these tricks, 2 dots are new to you, but you're going to get familiar with those. Okay. So these are the scores I get. There's one way that's much faster to do this, which is basically, 1 second. I can just use the model. I have linear classifier, and I can do decision function. Sorry. And of the first 10 points, which is basically 10. All right, and you can check that these are the same. This is how it works. You are probably going to compute these yourself. So it's very simple. matrix inversion, and you're going to see how to compute W and B later. It's pretty straightforward. Okay, so we said before that this classifier is missing 3 points, so my accuracy should be around 61 by 64. Okay? Since I'm lazy, I don't want to go and count the numbers. I can just use some functions. So the first thing is I want to get the predicted labels. Okay? So I call it ypred. And I have the linear classifier as going to predict. I'm going to predict on X. All right? So now I'm going to use the accuracy score from the matrix module of scikit-learn. Okay? So it's symmetric in a way that it doesn't matter the order, but not all metrics are symmetric, so be careful from that. Remember this. Accuracy score, and I will go compute the accuracy score between the true labels and the one that my model predicted. Oh, I didn't run this cell, sorry. Okay, there you go. You're getting the same accuracy. We're doing it right. But the accuracy is more like a summarizing matrix. Metric. I want to look at how many 0 labels are misclassified, how many 1 labels are misclassified. And in this case, that's where the confusion matrix comes. There are so many conventions, but we're going to assume that the rows of these matrix correspond to the true labels. Okay? So if I do confusion matrix between my true labels and my predicted ones, I get this matrix, okay? This means that label 0 is missed or misclassified 2 times. What's that? Oh, sorry. Okay. Yeah, I have to work on this. Okay, so this is the confusion matrix. It means that 2 elements of my class 0 has been misclassified as 1. And the second row, it means that 1 element of my class 1 was classified as 0. Okay, so this basically gives you how much or how many I missed per class. In this case, it's binary, simple, but sometimes you get 3 or even 10 when you work with the digits data set. Okay, and the confusion matrix, we can compute a lot of metrics based on the confusion matrix. For example, I want to compute the accuracy. Okay, in idea, how can I compute the accuracy using this matrix? I call it C. Okay, so the accuracy is defined how many points I got correct, divided by the total number. Okay, so the total number is just the sum of all the elements, and the number of correctly elements is going to be in the diagonal. Okay, so the number of, for NumPy, if I want to get the diagonal, just do diag C. There you go. And now I want to sum these, so you do np.sum. So this is the number of elements that I got correct. Now I want to divide it by the total sum, so just do np-sum C. Okay, you can check that np-sum is actually 64. There's another thing, which is I want to compute the accuracy per class. Okay. So, in this case, I want to see what's the percentage of elements that I get right for class 0 and the percentage that I get right for class 1. So in this case, I'm going to get 30 divided by 32 for class 0 and 31 divided by 32 for class 1. To do this, just remove this. To do this in NumPy, I will first try to sum the columns, because that will give me the total. In this case, it's 30 to 32, but I don't want to compute anything. Just want to PC do it. In this case, I'll do np-sum, and I'll do axes equal 1. Axes equal 1, it means that it is a sum, column-wise sum. Okay, I'm summing the columns. If I change it to 0, I'm going to get the sum of the rows. Okay, so it's 30 plus 1, 31 plus 2. But in this case, I'm interested in sum of columns. All right, and now I want to have the number of accuracy, or basically the ratio of correctly classified points per class. In this case, I'll just keep MPDIAG that I have used before. Okay? So I'm getting around 93% correct for class 0 and 97% for class 1. Okay? So this is what you call the rate accuracy per class. But if you do -1, which is the inverse, this is the missing or missed instances per class. Okay? So for class 0, I'm missing 6%. For class 1, I'm missing around 3%. Okay? So just a different name. Accuracy is the opposite, or 1 minus the missing rate. Perfect. Feeling good? Too fast? All right. So what we have done so far is everything you need for the KNN notebook. I saved you some space because I put all the helpers functions here, so you don't have to worry about those, but you have to import them to make sure that you're going to use them, okay? For those who want to volunteer and basically take the initiative, you can put your name here. Collaborators is not important in this assignment, but it's important in future assignments. Because we will be running some code checks, and if there's a huge overlap between you and another student and you did not mention their name, it will be considered plagiarism. And we had a lot of plagiarism cases last year, so probably the only class where we check plagiarism of code, so be careful. All right, so we'll be using a module of scikit-learn. It's called datasets. And this dataset will just provide you some toy datasets that we can play with. In this case, we're going to use an iris dataset, which is basically a flower. We have 3 types of flowers. And these points are projected into 2D. So this is 2D space data that we use to code the different attributes from the flowers. And we should have 3 types of flowers. Okay. I don't know how to pronounce those. Setosa, vesicolor, virginica. Okay. So you see that Setosa is easy to basically predict or learn, but not the 2 other ones. So the 2 other ones are going to be a little bit troublesome. And you can see that if we use a linear model, it's probably going to do well for Setosa, but not for the others. There's no clear linear boundary for the 2 others. Okay? The change here is that we're not only using 1x, we have xtrained and xvalid. So xtrained is the data we're going to use to teach the model, and xvalid is the one we're going to use to see how good the model is. You always want to keep something aside to check if the model generalizes well or not. Okay. So this is a very simple question. We're just looking at the number of elements of xtrain and the number of elements of ytrain. You can always check these. Okay. So we have 134 elements in our training data. We can look at xvalid. You're going to have 16. That's not too much, but it's enough for our case. Okay? So the same thing we have done before for a linear classifier or ridge classifier, we're going to do here. And in this case, we're just going to define the model. Okay? But in this, for this function, you'll be changing a parameter that's called number neighbors. Okay? So how many neighbors you want to consider in the model for the prediction of the label. I know this is black box or magic for you, but you're gonna understand everything. Okay? But for now, just look at it from a Python perspective. You have a class, you have some parameters to initialize it, so we're gonna do that. So in this case, I'll just do the model, k-neighbor classifier, neighbors, k-neighbors classifier. Okay, and I think the parameter was k-neighbors. To make sure that you get the parameters correct, you always go to documentation. So here, the default is 5. But for me, I'm just going to pass it as a parameter, so it's going to be num neighbors. Okay. So here I'm just doing some sanity checks. Blah, 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 blah. What's happening here? This is not fitted. Oops. Okay, so I defined the model, but I did not fit it using the training data. Okay, so in this case, I'll just do fit, and I give it the, or it's going to X-train, and then it's going to be Y-train. All right. Okay, so here we see the decision boundary. Before we had it for 2 classes, and in this case, we have 3 classes. Okay. If you don't like the colors, you can always go to helpers, and you can change it here, the CMap, the color map. Okay, and the color map you can just do pyplot CMap, and you can get a long list of colors here. It's up to you. Okay. All right. So going back to my notebook. So here I chose k equal 3, so I'm using 3 neighbors, but I want to look at different neighbors, okay? So in this case, I will just define my model. So I'll do model, build, model. You know what? I'm lazy, so I'll just copy this and build this. And in this case, the neighbor will be k. I'm trying different k from 3, 7, 9, something. And yep. Okay, so these are the decision surfaces when for different Ks. So this is 1, 3, 7, 5, 7, 9, 11. I would say you can see that the higher the number, the smoother, I would say. Yeah, probably smoother. The less abrupt the decision boundary is, or the smoother. Yeah, smoother is the right word. Mm-hmm. Okay, so this is the decision boundary based on one neighbor, which means that if I want to predict the label for a certain point, I just compute what's the nearest point to it. If it's label 0, I'll give it 0. If it's label 1, I give it 1.
I just asked for more detail. I said we could call it more detail.
What's smoother?
If that is smoother, we can call it
More detailed.
Yeah.
I'd say it's more detailed in 1. 2, yeah. So here we choose our resolution. So if you go to the helper functions, when we choose the mesh grid, we have changed in a certain resolution here. So let me go a little bit. Yeah, it's going to take some time, but you can change the resolution here. So in this case, just 2.5. Okay. So what happens here? Yep. So far we have been using X-train. We haven't used X-valid, okay? So in this cell, we're just going to evaluate on X-valid. You're going to try to use X-valid for the first time and not X-train. So in this case, I'll just copy this code here. Yep. Just copy this one here. I should paste that one, just do 1. Calls 1. I don't need this. I don't need this. And oops. Okay, so I'm training on the data points. In this question, I ask for nearest neighbor equal 1, but this time I'm gonna display the decision on valid, not trade. Yep. Here we go. And one thing here is that I can just do X. I know I'm getting messy here, but bear with me. Plot iris, and I'm gonna X valid, Y valid. Okay, so the function was plot. Helpers. There you go. Okay, so here I'm getting the scatter plot of the valid data points and the decision boundary from the training data. So I'm getting the blue ones almost perfect, but not the vesicle and virginica. Okay. So now we're going to do the same thing we had done before with confusion matrix, but here we have 3 classes. Okay, and so I'll leave this to you. It's the same thing we have done before. So if you go to the practice notebook, you're gonna just use the same code. And All right, so this is basically a sanity check. Here, we're going to do the same thing with confusion matrix, but for different values of neighbors. And you're going to see that for k equals 7, you get a perfect classifier. You're getting basically 100% accuracy. And yep, I guess you have all the ingredients for the remaining questions. Thank you. I'm aware I was fast, so you can always go back to. So the homework is KNN. Yeah, just there are some remaining questions, so you can try to answer. So we stopped at, we stopped at D, and you have all the way to F. I can hear you. Yes, I hope so. That's what I was told.
So this is homework 0 or this is homework 1?
This is 0. Yeah, there's no homework 1.
So this one's not graded.
No, this is not graded.
Do we turn it on Canvas after class or by tonight, or when do we turn it in by?
Just before Wednesday.
Okay.
Yeah. So homework 0 before Wednesday, because Wednesday will be releasing homework 1. Okay? If you want to.
Do you know where we turn it on Canvas? Is that open yet?
Yeah, I'll be creating that one so you can have it. Yeah. Thanks.
I just was wondering, for practice, if you scroll back up to the Lin-Alch inverse section. I think it was line like 22.
Thank you.